Hello and welcome to this revision session on forces on a charged particle, which is part of the magnetic fields topic in AQA A-Level Physics. So in this revision session we're going to be looking at some questions regarding forces on a charged particle. So we're going to have three different types of questions. Firstly, we'll have general check questions, which are basic questions designed to probe your understanding of the key concepts of the topic. You then have checkpoint questions. These are more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. Finally, you have assessment point questions, which are past paper examination questions which will mimic the types of questions found in public examinations. So let's start off with our questions. The first questions state, find the force acting on each of these particles. A helium nucleus travelling at 15,000 km per second when the field strength is 2.2 milliteslas. An electron in a magnetic field strength 1.3 teslas travels at 320,000 meters per second. Then a sulfate ion travels at 75 meters per second in a field of strength 0.14 teslas. So pause the video now, then unpause the video when you want to go through your answer. Right, for each of these, the equation is this is the general equation for a force on a charged particle. F equals BQV. So in the first one, it's 2.2 times 10 to the minus 3 times by 2 times by 1.6 times 10 to the minus 19, because a helium nucleus has a charge of plus 2, times by 15,000 times 10 to the 3 is 1.056 times 10 to the minus 14 newtons. In our second question, F equals BQV, so it's 1.3 times by 1.6 times 10 to the minus 19, the charge of an electron, times by 320,000, so it's 6.656 times 10 to the minus 14 newtons. And then finally, F equals BQV, so it's 0.14 times by 2 times by 1.6 times 10 to the minus 19, because there's a charge of 2, times by 75, so it's 3.36 times 10 to the minus 18 newtons. Our next question says, why would a neutron moving through a magnetic field perpendicular to its direction of motion not experiencing a force? Then, for question 2, in which direction will the force due to the magnetic field act on the electron in this diagram? And then finally, find the force that acts on a particle with a charge of 3.2 times 10 to the minus 19 coulombs travelling at a velocity of 5.5 times 10 to the 3 meters per second perpendicular to a magnetic field of flux density 640 milliteslas. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the first answer is only charged particles will experience a force from their magnetic fields. Second question, you would use your left-hand rule. Now remember, the current is pointed in the direction of current flow, which is the opposite direction to the electron motion. You can then have your magnetic field pointing out of the page, so therefore the force, which is the thumb, will be acting upwards. Then finally, in the third question, F equals BQV, 640 times 10 to the minus 3, times by 3.2 times 10 to the minus 19, times by 5.5 times 10 to the 3 is 1.1 times 10 to the minus 15 newtons. The next question says, each of these cases describes circular motion due to the effect of a magnetic field on a moving charged particle. The track of an electron has a rate of 2.5 micrometers in a field of 3.3 teslas. How fast is it moving? Second question, a particle is moving at 1.57 times 10 to the 6 meters per second in a magnetic field of 0.39 teslas. The radius of the motion is 42 millimeters. Find the charge to mass ratio. Then an electron is travelling at 0.1 c in an experimental solenoid with a magnetic flux of density 24 teslas. What will the radius of rotation be? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're rearranging our equation, which is F equals BQV, which equals mv squared over r. So therefore, r equals mv over bq. So v equals rb, barbq over m. Pop in all the values, and you get 1.45 times 10 to the 6 meters per second. The second question, again, r equals mv over bq. We want the charge to mass ratio, which is q over m. So we rearrange it and make q over m the subject. So q over m is equal to v over br. We then pop in our values and we get 9.58 times 10 to the 7 coulombs per kilogram. And then finally we want our radius of rotation. Once again, r equals mv over bq. So you then pop in all your values. Now remember, an electron's mass is given to you on the equation sheet. It's 9.11 times 10 to the minus 31. We know that c is 3 times 10 to the 8. So you pop in all your values and you get 7.12 times 10 to the minus 6 meters. Our next question says, The magnetic force BQV causes an electron to travel in a circle in a uniform magnetic field. Explain why this force does not cause an increase in the speed of an electron. Then, an electron beam is produced from an electron gun in which each electron is accelerated through a PD of 1.6 kilovolts. When these electrons pass at right angles through a magnetic field of flux density 8.0 milliteslas, the radius curvature of the electron beam is 0.017 meters. Determine the specific charge of the electron. Then two particles, an alpha particle and a beta particle, are travelling through a uniform magnetic field. They have the same velocity and their velocities are at right angles to the field. Determine the ratio of the mass of the two particles, the charges of the two particles, the forces created by the magnetic field on the two particles, the radii of the circular orbits of the two particles in the magnetic field. Then, a moving charged particle experiences a force in an electrical field and also in a magnetic field. State two differences between the force experienced in the two types of field. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, the force is at right angles to the velocity and does no work on the electron, since work is equal to force times by the distance moved in the direction of the force. As no work is going to be done on the electron, the kinetic energy of the electron is constant, as is the speed. In our next question, we know that the kinetic energy is equal to EV. So therefore, we can say R is equal to mv over bq. And we also know it equals to Q over M. So we can pop in our values in, rearrange the values, pop it all through, we get 1.7 times 10 to the 11 coulombs per kilogram. In our next question, we then do the alpha particle, which is going to be 4 times by 1.67 times 10 to the minus 27, which is the atomic mass unit, value in kilograms, given to you on the equation sheet, over 9.11 times 10 to the minus 31, the mass of an electron or a beta particle, so it's 7,300. The charge of the two particle, well, the alpha has a charge of 3.2 times 10 to the minus 19, the beta or the electron is 1.6 times 10 to the minus 19, so that ratio is to 2. Our force is going to be just the ratio of the charges because it's F equals BQV and B and V are constant in this question. So therefore, it is just 2. Now the radii will be equal, R is equal to MV over BQ, but again, B is going to be a constant, so therefore we can ratio the two values. So therefore it's 7,333 divided by 2, which is 37,000. Then in the last question, the force is always at right angles to the direction of the magnetic field and is in the same direction in the electrical field. Now the force is proportional to the velocity of the electron in a magnetic field, but it doesn't depend on the velocity of the electron in an electrical field. Our next question says, the figure below shows the path of an electron as it travels in the air. The electron rotates clockwise around a uniform magnetic field into the plane of the paper, but the radius of the orbit decreases in size. Firstly, explain the origin of the force that causes the electron to spiral in this manner. Then explain why the radius of the circle gradually decreases. At one point in the path, the speed of the electron is 1 times 10 to the 7 meters per second and the magnetic flux density is 0.125 teslas. Calculate the force on an electron at this point due to the magnetic field and the radius of the path at this point. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the electron is charged, okay, so the magnetic field of the moving charge will interact with the uniform magnetic field. Secondly, the electron ionizes atoms as it moves and therefore loses kinetic energy. So the speed of the electron decreases and the radius will also decrease because R equals mv over bq. And then finally, in these next two, F equals BQV, so it's 0.25 times by 1.6 times 10 to the minus 19, the charge of an electron, times by 1 times 10 to 7 is 4 times 10 to the minus 13 newtons, my apologies. Then we know R is equal to mv squared over F, we rearrange it, F equals mv squared over R, pop in all the values, work it all through, and we get our answer out to be 2.3 times 10 to the minus 4 meters. Next question says, explain why the stationary charged particle in a magnetic field does not experience a force. Then calculate the maximum magnetic field experienced by an electron travelling at the speed of 6 times 10 to the 5 meters per second in a uniform field of flux density 0.20 teslas. Then, a particle of charge plus 2e describes a circle of radius 2.5 centimeters in a uniform magnetic field of flux density 130 milliteslas. Calculate its momentum. So pause the video now, then unpause the video when you want to go through your answer. In this first one, the force is given by F equals BQV. So V is 0, F will be 0. Again, the second question, F equals BQV. We pop in all the values. Remember, the charge of electron is 1.6 times 10 to the minus 19, so it's 1.92 times 10 to the minus 14 newtons. And then finally, R equals mv over bq, so momentum is mv, so mv equals bqr. Pop in all our values. Remember, it's 2 times by 1.6 times 10 to the minus 19 is 1.04 times 10 to the minus 21 kilogram meters per second. The next question says, electrons ejected from an electron gun at a speed of 1.4 times 10 to the 7 meters per second enter a magnetic field of flux density 2.4 milliteslas acting at 90 degrees to the beam. Determine the radius of curvature of the path followed by the electron beam, given that the specific charge of the electron is 1.76 times 10 to the 11 coulombs per kilogram. Calculate the speed of an antiproton created in a high-energy collision if the radius of the curvature of its track is 0.11 meters and the detector's magnetic field strength is 3 teslas. A charged particle moving at right angles to a constant magnetic field follows a circular path. Show that the radius of the curvature of the particle's path is directly proportional to its momentum. And then particles of mass m, charge q, travel in a circular path of radius r and speed v in a magnetic flux density b. How many quantities m, q, v, r and b, if increased one at a time, would increase the radius of the path? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know r equals mv over bq. So therefore it equals v over b times by q over m. We'll just rearrange that to get q over m in there, the charge to mass ratio. Pop in all the values and we get 0.033 meters. Next one, we rearrange it to make v the subject. V equals bqr over m. We're given the mass of the antiproton, which is the same as the proton on our equation sheet, is 1.67 times 10 to the minus 27 kilograms. Pop all the values in and we get 3.2 times 10 to the 7 meters per second. We know F equals mv squared over r and equals bqv as well. So we can therefore rearrange it, equate the two, and have r equals mv over bq. Now, because in this question q and b are constant, r is proportional to mv, so r is proportional to momentum. Finally, we know r is equal to mv over bq. So increase in m and v would increase r, but increase in b and q would decrease r. The next question says, mass spectrometers measure the mass and relative concentrations of atoms and molecules. They're used for all kinds of chemical analysis. Atoms from a sample are ionized and accelerated through a potential difference. They pass through a velocity selector and emerge with the same speed before entering a uniform magnetic field. Each different ion is then deflected different amounts onto the detector. Suggest why it's important that all ions have the same speed in a mass spectrometer. Calculate the radius of curvature for a single ionized carbon-13 ion travelling at a speed of 8 times 10 to the 4 meters per second in a mass spectrometer where there's field of flux density 0.75 teslas. The mass of the ion is 2.16 times 10 to the minus 26 kilograms. And then estimate the radius of curvature for a single ionized carbon-14 ion in the same mass spectrometer. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, we know r equals mv over bq. V and b happen to be a constant, so therefore r can only be proportional to the specific charge of the ion only. In our next question, r equals mv over bq, we pop in all our values from the question. So we know what m is, we know what v is. Now we can work out what m is because we know it's carbon-13, and we also know the mass of a single atomic unit, so you can work it through like that. Pop in all the values again for b and q, and we get 0.0144 meters. This next one, we know r equals mv over bq. Now we know the only thing changing is our mass. We're going from carbon-13 to carbon-14, so the ratio change is going to be 14 over 13. So we multiply it by that value and we get 0.0155 meters. The next question says, Figure 1 shows part of an evacuated tube that is used to determine the specific charge for an electron. An electron beam is directed through two parallel metal plates X and Y. In the region between the plates, a magnetic field is applied perpendicular into the plane of the diagram. An electric field can be applied in this region by applying a potential difference between the plates. Figure 1 shows the path of the electron beam when the magnetic field is applied and the PD between X and Y is 0. Explain why the fit path followed by the electron beam of the magnetic field is a circular arc. Show that the speed of the electrons is given by V equals BER over m, where r is the radius of the path of an electron and b is the flux density of the magnetic field. Then a PD is now applied between X and Y without changing the flux density of the magnetic field. V is adjusted until the electron beam is not deflected, as it travels in a region between the plates. Determine an expression for the speed V of the electrons in terms of V, B and the separation D of the metal plates. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know there's a constant force which always acts right angles to the path or the motion or the velocity of the beam. So because the force is at right angles to the magnetic field and electron motion, it'll form a circular path. We know R equals mv over bq, so therefore V equals BER, because we know E is Q because it's just the charge of an electron, over m. And finally, we know BeV, which is going to be the force on the electron, because E equals Q, is equal to EV over D, so therefore it links into the field equation there, so V equals V over BD. Our next question says, an electron travelling in a vacuum at speed of 3.4 times 10 to the 7 meters per second. The electron enters a region of a uniform magnetic field of flux density 3.2 milliteslas. The initial direction of the electron is at an angle of 30 degrees to the direction of the magnetic field. When the electron enters the magnetic field, the component of its velocity, normal to the direction of the magnetic field, causes the electron to begin to follow a circular path. Calculate this component of the velocity, the radius of the circular path, state the magnitude of the force, if any, on the electron in the magnetic field due to the component of its velocity along the direction of the field, and then use this information to describe the resultant path of the electron in the magnetic field. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it's the component of the velocity. So it's 3.4 times 10 to the 7 times by sine 30 because of the angle 30. So it's 1.7 times 10 to the 7 meters per second. The next question, we know R equals mv over bq. We know the mass of the electron from the equation sheet, 9.11 times 10 to the minus 31. We know all the other values, including v, which is the component, not the overall value. So it's 0.030 meters. There's going to be no force acting on the electron because it's at 90 degrees to the actual the field at that point. And then the last one, it's therefore going to form a helix or a coil or a circular path because you've got the centripetal force acting upon it. The next question says, calculate the speed of an antiproton created in a high energy collision if the radius of the curvature of its track is 0.11 meters and the detector's magnetic strength is 3 teslas. Then a charged particle moving at right angles to a constant magnetic field follows a circular path. Show that the radius of the curvature of the particle's path is directly proportional to its momentum, and then particles of mass m and q travel in a circular path of radius r and v in a magnetic field of flux density b. However, the quantities m, q, v and b, if increased one at a time, would increase the radius of the path. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first question, we know R equals mv over bq. Therefore, V equals BQR over m. We know that the mass of the antiproton is the same as the proton, 1.67 times 10 to the minus 27. We know the charge of the antiproton is the same magnitude as the proton, 1.6 times 10 to the minus 19. Pop in all the values and we get 3.2 times 10 to the 7 meters per second. In this next question, we know BQV equals mv squared over r equals the force. So BQR equals mv. So therefore, R equals mv over bq. As B and Q are constant, R is proportional to mv. And then finally, we know R is equal to mv over bq. So increasing m and v would increase R, but increasing B and Q would decrease R. Next question. State two situations in which a charged particle will experience no magnetic force when placed in the magnetic field. Then a charged particle moves in a circular path when travelling perpendicular to a uniform magnetic field. By considering the force acting on the charged particle, show that the radius of the path is proportional to the momentum of the particle. Then a cyclotron is a circular particle accelerator. In a particular cyclotron, the flux density of the uniform magnetic field is 0.48 teslas. Calculate the speed of the proton when its radius of its path inside the D is 190 millimeters. Then calculate the time taken for this proton to travel at a constant speed in a semicircular path of radius 190 millimeters inside the cyclotron. So pause the video now, then unpause the video when you want to go through your answers. Right, so the two conditions are when the charged particle is at rest or not moving relative to the field, or if the charged particle moves parallel to the magnetic field. In our next question, BQV equals mv squared over r, so therefore R equals mv over bq. B and q are constant, so R is proportional to mv. In our next question, we know R equals mv over bq, so V equals BQR over m. Pop in all the values. You know the mass of a proton, you know the charge of a proton from the equation sheet, so you pop them all in and you get 8.7 times 10 to the 6 meters per second. Now, because we're moving in a semicircular path for the next question, the length of the path is the length of the semicircle, which is pi r. So the time taken is going to be the length divided by the velocity. So it'll be pi r over v. So it's pi times by 0.19 over 8.74 times 10 to the 6 is 6.8 times 10 to the minus 8 seconds. The following question says auroras occur above the Earth's pole when charged particles collide with gases in the upper atmosphere. These collisions provide tiny flashes that fill the sky with light as shown. Collisions between electrons and oxygen atoms cause the emission of green light. Calculate the velocity of electrons that cause a green light of wavelength 560 nanometers to be emitted from the oxygen atom. And then radio waves are produced during an aurora. Electrons moving in a circular path in the atmosphere emit radio waves. The frequency of the emitted radio waves is the same as the frequency of the rotation of the electron. An electron with speed 1,650 km per second is moving perpendicular to a magnetic field with flux density 48 microteslas. A radio station is broadcasting at a wavelength of 220 meters. Deduce whether the radiation emitted by the electron would interfere with the signal from the radio station. You should include the calculation for the radius of the circular path of the electron. So pause the video now, then unpause the video when you want to go through your answers. Right, for the first one, we know F is equal to C over lambda, so it's 3 times 10 to the 8 over 560 times 10 to the minus 9 meters, so it's 5.36 times 10 to the 14 hertz. We know the energy of a photon is equal to HF, so 6.63 times 10 to the minus 34 times by this value of F, so it's 3.55 times 10 to the minus 19 joules. We there finally know that V is equal to the square root of 2 times by the mass of, by the kinetic energy, okay, divided by the mass, so therefore it's going to be 2 times by this 3.55 times 10 to the minus 19 over 9.11 times 10 to the minus 31, so it's 8.83 times 10 to the 5 meters per second. In the second question, we know the momentum is going to be the mass of the electron times by its velocity. So it's 9.11 times 10 to the minus 31 times by 1.65 times 10 to the 6. So it's 1.50 times 10 to the minus 24 kilogram meters per second. We know R equals mv over bq. So with this information, we know R is equal to 0.196 meters. We know that the wavelength, therefore, is going to be c over f. Now we can work out what our value of f is going to be, because we know that c is going to be 3 times 10 to the 8, but then also that the frequency is going to link into how many rotations you would have in a second in terms of its when it goes through. So we would know that would be 1.34 times 10 to the 6 hertz. So therefore our wavelength is going to be 224 meters. Now it would cause interference because the radio station is emitting at 220 meters. So therefore it's a very similar wavelengths, so therefore the electron would cause interference with our radio station broadcast. So again, just to remember, how do you get that frequency? Well, you can work it through, because you can say, well, frequency is 1 over the time period, and as you can work out the time period, because we have our radius of the actual circular path, you can work out how quickly it's going to rotate through that. So you can work it through, working through to get 1.34 times 10 to the 6 hertz. So that brings then to our revision session today. If we've been successful and we've learnt in this lesson, we should be able to calculate the magnetic force on charged particles moving in a magnetic field, detail the direction of the magnetic force on positive and negative charged particles, and finally calculate the magnitude of the magnetic force produced in the circular path of particles and applications. So thank you so much for attending this revision session on forces on a charged particle, which is part of the magnetic fields topic in AQA A-Level Physics.